See. It's a good pleasure to have today Abdel Fatih, who will give several lectures starting from today. And the first one is on weekend theory on metric spaces.
It's all on weekend theory. And metric spaces, lecture 1, 2, 3. Okay, so what I'm going to do here is, so you know that you have for the Hamilton-Jacobi equation, the viscosity theory is the one that works, especially in the case where the Hamiltonian is convex in the momentum. So people have been trying to get generalization away from an open set in Rn or a manifold, and the usual theory of viscosity solution uses comparison. And I think most of people try to extend this point of view of comparison with test functions. But what I realized is that there is another way. So because the Hamiltonian is convex in the momentum, it has an associated Lagrange. And this allows you to define action for curves. I'll explain the thing, but I'm trying to motivate things a little bit. So once you have action for a curve, you can define the minimal action to go from a point A to a point B. And we are going to reconstruct the whole theory just knowing the minimal action. So from this, we are going, well, of course, defining such solution is not the problem, but we are going to define solution and also the uniqueness set known as the Aubry set only in terms of minimal action. So, and then you can just get out of the manifold or open set thing. It's just, you can work it on any metric space, let's say compact for the moment to avoid technicality. So this is the program, and I would like to dedicate, it's not working. Econolfi, who started, in fact, the whole idea of metric methods and is a master of the metric methods. So let me first recall the weight KM theory on Lagrangian systems. So we start with a compact Riemannian manifold. And we suppose, so there is a metric because it's Riemannian, and the norm is the square root of the scalar product of the vector tangent. So the J length, you know how it is. It's to define the length of a curve, you integrate the norm of the speed along the curve, and the distance is obtained by minimizing lengths of curves between the 2 points. Okay, so this distance does indeed define the topology on M. And now we come to what is the Lagrangian, but I will restrict here to Tonelli Lagrangian to be able to say things a bit more easily. So Tonelli Lagrangian is a C2 function on the tangent space. So it's a function, real valued function of position and speed. Okay, and we are going to ask not only that it's convex in V, but also the second partial derivative in V is positive definite, so it's strong convexity. The second thing is the uniform superlinearity. We want it to grow faster than any linear thing in V. Okay, so this is just L of x v divided by the norm of Vx goes uniformly in x to infinity when the norm of V goes to infinity. Okay, so you can write the second condition due to the compactness as for every k, L of xv is larger than k times the norm plus a constant which depends on K. Okay? Simple exercise to show that this is the same condition. Now you define the action by integrating the Lagrangian along the speed curve. Action of a curve is just the integration of the Lagrangian along the speed curve. Okay? And now you define for a time t fixed, positive time, you define h sub t xy as the minimum action needed to go from x to y in time t. Okay? By Tonelli's theorem, it's achieved, but don't really need to discuss that here. Okay, so what is the Manier potential? Now, so this is a minimal action to go in time t. Well, you would like to take the minimal action independent of t, for all t. But now you have to be careful because if you change here by a constant, okay, the minimal action will change easily. But here you have to be careful. So it will depend on a constant c, which is a normalization. You can always add a constant to the Lagrangian, and you are not going to get very different things. Okay, but here, if you take the inf for t of ht of xy plus tt, it depends on c. Okay, and so this is what is the Manier potential for the value c. Phi c xy is the infimum of action to go from x to y in any time, but that you modify the Lagrangian by adding c to it, or you modify the minimal action of the Lagrangian by adding ct. Okay. And what is the Peyer's barrier? So phi c is the infimum, and h of xy, the Peyer's barrier between the 2 points, is defined as the lim inf of this quantity as t goes to plus infinity. Okay, so the inf is less than the limit. Now, here is a proposition. I mean, I'm not going to prove all these things, but I'm just recalling because after that, we will need some comparison to the situation to see that things go well. Works well. There is a unique constant c of 0 such that phi c is identically minus infinity for c strictly less than c of 0 and is finite everywhere for c larger than c. Okay? If you have an action which become between 2 points which become arbitrarily negative, you can just keep on going around the curve which has negative action, and then you will get more and more negative. So as soon as you have a closed curve with negative action, then the phi c is minus infinity. So this constant is called the Manier critical value, and in fact it's finite because you can estimate it. You can give an estimation. Remember, M is compact, so this inf is finite. And this one is finite also because L is superlinear and M is compact. Now, for the Peyer's barrier, in fact, you are minus infinity for C strictly less than C. And it's plus infinity uniformly for C larger than C0, and it's finite everywhere for C equals C0. Okay? So this is what you have for this classical case. And in fact, the Manier potential is a semi-metric, and moreover, it is bounded by a constant times the distance. So it's going to be continuous. What do I mean by a semi-metric? Yeah, semi-metric on a set is a function from x times x, sorry, there was a misprint, into R. Note, I'm not assuming that the values of phi are non-negative, okay, which satisfy two things. Phi of xx is 0, and the triangular inequality, but be careful, you need the order. It's not symmetric. By definition of semi-metric, I should have probably said non-symmetric semi-metric, but it's okay. So the triangle inequality now has to be understood in that way. So you go from x to z, okay? What is you can think of as the action is less than the action of going from x to y plus the action going from y to z. And of course, it depends on the order. Okay, so it's not a metric because you can have 2 points at distance 0 and it's not symmetric. Okay. And moreover, it can take negative value. So the projected Aubry set, so it's a set in M, is a set where the pairs barrier from x to x is 0. Okay, so that means you can go from x to x, okay, with arbitrarily small action for arbitrarily long times. Okay, because hc of xx is the limit when t tends to plus infinity of hc of xx plus ct. So you can go with. Now, of course, it's empty for c different from c0 because hc is either plus infinity identically or minus infinity identically. And you can show that for c0, for that case, it's not empty. Okay. Now, when you look at the definition of phi c at the infinity of the ht plus ct, and the definition of hc as the limit inf, you think that it seems impossible to get hc solely from the knowledge of phi c. How can you get the lim inf from an inf? Okay, so this is not possible, but in fact, that's what we are going to do. And of course, I mean, it's because we know it for every pair of points, and we have, some continuity assumptions and things. Okay. And it's a 20 years old idea due to Antonio to obtain the Aubry set from just phi c0. So the Aubry set is the set of points where h c of xx is 0. So you can already, you knew 20 years ago that you could do it at least for the Aubry set. Okay, but we are going to show it for the whole of hc0. And we will also give a way to obtain the viscosity solution or KAM solutions, okay, just from the Manier potential. Okay, this is not clear from the definition either. Well, for sub-solution it's obvious, but for solution it's not so clear. So let me come to the viscosity solution. The Hamiltonian associated to L is given by the Fenchel or Fenchel-Legendre or Legendre-Moreau or Moreau-Fenchel. Choose your name by the equation h of xp is the sup of pv minus L of xv. Okay, p is a covector, so it's linear form. And since L is Tonelli, the Hamiltonian is finite and continuous, and the sup in the definition is attained because it's of the superlinearity. So in fact, it's not a sup, it's a max. And moreover, H is also Tonelli, meaning that it's convex in the momentum. In fact, the second partial derivative. Well, first it is C2, you can show it is C2. Then the second partial derivative of H with respect to the momentum P is also positive definite, and it's superlinear. So the Hamilton-Jacobi equation, stationary, going only to speak of stationary solution, is H of xd dxu equals C. I have a reason to do that because by taking the Magne potential, I forgot that there existed a time. I'm not going to be able to reconstruct time. I never claimed that. Okay? So this is the Hamilton-Jacobi equation where we are speaking only of the global Hamilton-Jacobi equation. So U is a map from M into R and C in R. A classical solution is when U is C1, but because M is compact, there is hardly C1 solution to this equation. So this is why you introduce viscosity solution. Now, it's easy to define viscosity solution in this setting. It's a Lipschitz function such that h of x dxu is less than C for almost every x in M. Of course, it's also a subsolution in the sense of comparison that you do usually for viscosity, but because of the convexity of H in P, these subsolutions are the same as the subsolution, the viscosity subsolution, the same as this one. Okay? So, in fact, there exists a subsolution if and only if C is larger than C0, where C0 is a Magne critical value. And for C larger than C0, a function U is a subsolution, okay, of the Hamilton-Jacobi equation at level C if and only if Ui minus Ux is less than phi C x and y. So what does this express? It expresses that U is a Lipschitz function with respect to phi C, Lipschitz, but for phi C, not for the distance, with constant 1. You should think of it like that. Okay? Of course, you don't have absolute value because it's not symmetric. Usually when you define Lipschitz function for the distance, it's equivalent to this because the distance is symmetric, so you can just switch x and y and get the absolute value. So moreover, for C larger than C0 and x in M, the function phi Cx dot, so the function where you fix the first argument to x, and the function of the second argument is a subsolution of h of x px. Okay? So you know that the distance function to a point is a Lipschitz function. So it's exactly the same type of thing. There is also a concept of viscosity solutions, but it would take us too much time to explain it, to give the viscosity point of view. But in fact, we can define them in an equivalent way in this setting as using the Laxolenic semi-group, which is defined as follows. For a bounded function, U from M into R, and T positive, you define the function TCTU by TCTU at X is the infimum for all Y in M of the action corresponding to the level C in time T. Well, you penalize it by U of Y. Okay, to have the dependency on U. Okay. So these functions are all continuous, even if U is not, for T positive. Okay. And theorem, the family has a common fixed point if and only if C equals C0, because we are on M compact. The compactness plays a role here. Okay. And the viscosity solution, in fact, are precisely the common fixed point. If you know what is a viscosity solution, you can show this fact. Okay. And how do you find viscosity solution? Well, you know that H is finite at the level C0, then H of C0x dot, so you fix the first argument and look at the function of the second argument. This is always a viscosity solution. Okay. Now I remind you that thing so that if you know about it, you can see the analogies. But from now on, we don't have to know anything except whatever you learned in your real and school. Okay. Okay. So we are going to consider a compact metric space XD together with a continuous semi-metric on X. So D, I'll try to call D the distance rather than the metric. So we don't get confused with semi-metric. Okay. Semi-metric, let me remind you, is a function from X to X, phi, with value in R such that phi XX is 0 for all X, and you have the triangular inequality, phi XZ is less than phi XY plus phi YZ. Okay, that's all we have in our hand, and we are going to develop the whole theory from there. So we do not assume the semi-metric non-negative. However, 2 implies phi of xy plus phi of yx larger than phi of xx, sorry, which is 0. Do the correction, so you will have access to the slides corrected later today. Okay, so in fact, if you symmetrize phi by adding phi xy and phi yx, it's always non-negative. It also implies that there are 2 ways to symmetrize phi. Either you add phi xy to phi yx, or you take the maximum. This is also symmetric. And because the sum is non-negative, one of the 2 terms is non-negative, so the maximum. Okay? Now, the example to keep in mind is X is a compact manifold equipped with a Tonelli Lagrangian, and phi is phi C0, the Manier potential. And this one is not always non-negative. We are not assuming phi non-negative. Now, I'm going to give you a kind of some trivial examples of semi-metric to see that it's kind of very general. It doesn't have to come from a Tonelli Lagrangian. So the first one is to take identically 0. Of course, it doesn't do anything, so it's not interesting. The second thing, any distance on X is a semi-metric. Okay. If you have a function from X into R, then you can define U hat, the semi-metric, by U hat xy is UY minus UX. It's kind of degenerate metric because all triangular inequality are equality. Okay? And it's also the case for the absolute value of U hat. Okay? It will also satisfy the triangular inequality. Now, if you have U, which is a function, and phi, no, it's not an arbitrary. Yeah, you can define phi sub U of xy as phi of xy modified by U in the following way. Okay? It's kind of a classical thing. Okay? You think of this as kind of cocycle, and this is a co-boundary. If you know a little bit about homology. So if phi is a semi-metric, phi sub U is a semi-metric. So you can get different semi-metrics like that. Now, for example, if you take the zero metric, semi-metric, what is zero sub u? It's your hand. If you have any function, you can phi on x cross x with value in R. You define its Chech, phi Chech, okay, as a function where you switch the x and y. Okay. So if phi is a semi-metric, so is phi Chech. If you have two semi-metric, then the maximum is a semi-metric, okay, where the maximum of phi1, phi2, xy is the maximum of phi1 of xy, phi2, xy, okay? And of course, phi max is also the maximum of phi and phi change, by definition of phi change. And it's always non-negative. Okay, and this follows from the fact that phi of xy plus phi of yx is larger than phi of xx by the triangular inequality, that phi of xx is 0. Now, if you have two semi-metrics, you can also take the sum. It's a semi-metric, okay, and the sim f sim, not phi sim, is the sum of phi and phi change. Again, it's non-negative. Okay, another interesting example is the following. So if you have a semi-matrix on X, you can define a semi-matrix on phi hat on the space of probability measures on X. Okay, in the following way, phi hat nu is the infimum over all plans gamma of the integral over x times x of phi xy d gamma of xy. What is gamma? Gamma is a probability measure on x cross x whose first marginal is mu and second marginal is nu. Marginal means that you look at the projection. Next. The first one. So this is P1. So you have the image of gamma by P1 is mu, and same thing with P2, you get mu. Okay. So in the sequel, phi is a continuous semi-metric on the compact space Xt. And it is convenient to note in that case that phi max is also continuous and a continuous semi-metric, which is symmetric and everywhere non-negative, as we said. Moreover, it vanishes on the diagonal of x cross x because both terms are phi x. Okay, well, it's semi-metric to vanish on the diagonal anyway. Okay. So I'm going to define first phi subsolutions because it's less in digest than to start to define the Payer's barrier and the solution, but it's probably not the logical order. I should define Payer's barrier, hope reset, and then solution, subsolution, and solution at the same time. But I prefer to start with phi subsolution, so it goes easier. So what is a phi subsolution? It's a function u from x to r such that u of y minus u of x is less than phi of xy. Okay, so in your head, this is the Lipschitz function for phi. It's phi Lipschitz with Lipschitz constant 1. Okay, and it has to be without absolute value because phi is not symmetric. So this equivalent, of course, to u of y is less than u of x plus phi of x. Now we are going to denote by S sub phi the set of phi subsolutions. Note that the set S sub phi of phi subsolution depends only on phi and not on the choice of the distance d defining the topology on X. The topology does not intervene here for the definition of subsolution. Okay, of course, you are going to ask phi to be continuous, so you can say a few things interesting about the subsolution. So we compute phi subsolution in some of the examples we have given. So if u is a continuous function, the semi-metric u hat is u hat of xy, u of y minus u of x. And I'm going to show that the subsolution are just the translate of u waveforms. It should be clear from, okay, from the definition, maybe I come here. If I add to C a constant, I remain a subsolution. So V, I want to show that V is a subsolution of u hat if and only if V minus u is a constant function. So if V minus u is a constant function, from what I said, V is a subsolution, phi subsolution. But now let's prove the converse. Suppose V is in a subsolution. So it has to satisfy Vy minus Vx is less than u hat of xy, which is u of y minus ux. I can rewrite this as Vy minus uy is less than Vx minus ux. Okay? But now I can symmetrize the situation in x and y, so I must have equality. Okay? And so that tells me exactly that V minus u, a constant. Okay? Now let's consider the case where X is a closed interval in R, okay, with the usual distance d on the interval, which is given by the absolute value, and suppose that u from X to R is a C1 function. Okay? The case when u prime is not of constant sign is more tricky, and I don't want to get into it. So I'm going to keep things simple and assume that u prime is non-negative everywhere. Okay? So u is non-decreasing. Now, I'm going to look at semi-metric, the absolute value of u hat. Okay, absolute value of u hat, xy, is the difference of u of y and u of x in absolute value. And I'm going to show that the subsolution for absolute value of u hat are the Lipschitz function. So Lipschitz function on the interval in the classical sense, such that the absolute value of the derivative is less than u prime x for almost all x in y. Because the function is Lipschitz, the derivative exists almost everywhere. Okay, so this makes sense. Now, I have V is a subsolution if and only if Vy minus Vx is less than absolute value of u hat at xy, which is absolute value of uy minus ux. Okay, so this has to be true for all xy in I. And by considering only the case x less than y, I get, in fact, that Vy minus Vx is less, in absolute value, is less than uy minus ux. Okay? And so this tells me first that V is Lipschitz. Okay. because U is Lipschitz, C1, so it's Lipschitz. And the function V is differentiable almost everywhere. And if we look at this inequality, it tells us, by passing to the limit, that at every x at which V prime x exists, the absolute value of V prime x is less than V prime x. So almost everywhere. So this proves the inclusion that the subsolution is contained in the set of Lipschitz functions V with absolute value of V prime x less than V prime x almost everywhere. Now, from the converse, okay, so you suppose you have the inequality, absolute value of V prime x is less than U prime x for almost all x in I, and then you get, of course, that Vy minus Vx is less than the integral, absolute value of the integral of the derivative. And because we are assuming x is less than y, it's less than the integral of the absolute value, so it's less the integral of U prime, which is then Uy minus Ux, which is the solution. Okay? Now we can take phi equal t as a semi-metric on x. Okay? So it's not difficult to see in that case that the subsolution is exactly the set of Lipschitz function with Lipschitz constant 1. Okay? I said that the subsolution were the function which were Lipschitz for the semi-metric, in this case, the semi-metric. So it's exactly that. And if you multiply instead of, okay, and let's look at this one. If you have a distance for any alpha between 0 and 1, e to the power alpha is also a distance, which defines the same topology. So here is the game I can play. I can take this metric, the alpha, this distance as the distance on x, and take as semi-metric the distance v. Okay? Again, the set of subsolution is a set of functions which are Lipschitz with Lipschitz constant 1, since, as we said, the set of subsolution of phi depends only on phi. Okay. Back to the case before. Now, of course, if in 3, instead of taking d, you take k times d, the set of subsolution will be the set of Lipschitz function for d with Lipschitz constant is k. That most k. Okay. Now, let me come to the properties of subsolution. So the family of subsolution is equicontinuous. Okay. And this follows from the inequality that we will show absolute value of Uy minus Ux for U subsolution is less than phi max xy, okay, for all xy. And because this one is continuous and 0 on the diagonal, okay, the modulus, you can choose it as a common modulus of continuity at the point x for all the subsolutions. Okay, the family of subsolution is stable under pointwise convergence. It's a convex subset, and it is stable under addition of constants. Moreover, if we have a family of subsolution, okay, then either the infimum is minus infinity, or the infimum is finite everywhere and is a subsolution. And same thing for the subfimum. So the infimum of subsolution is a subsolution unless it is identical minus infinity. Now, for every x0 in x, the function phi x0 dot, so you put x0 in the first argument, is a subsolution. And if you want to take it as a function of the first argument, well, you have to put a minus sign here to obtain that subsolution. Okay? So let me prove that. So this inequality here, which characterizes the subsolutions, okay, implies that ui minus ux is less than phi max because phi max is larger. Okay? And of course, phi max is symmetric, so we can put the absolute value. Okay? So this is the proof of that. And the equicontinuity now follows from the continuity and the fact we don't really need the compact set because, I mean, it's equicontinuous at every point, and because X is compact, it's uniform. Equicontinuous, but you are hardly going to use the uniform equicontinuity. Okay. Now, convexity and stability follows from this equivalent definition of subsolution. Okay. If you take a convex combination of such inequality, you get an inequality of the same type if you add a constant also. Okay. Oh, I forgot here, maybe it's probably not the right. Two also is the stable under pointwise convergence follows also from the same inequality. Okay, if family converge pointwise to U, you just have the same inequality. Now, 4. So we want to look at the infimum of a family of subsolution. So each of them satisfies that. And when you take the infimum, which can be finite or minus infinity, you just get the same inequality. If at some point it is minus infinity, because phi is finite everywhere, then it is identically minus infinity. If at some point it's finite, then here it's finite also. Okay. Now, and when finite is when phi. Okay, so that's what I said before. And of course, in this last case, we satisfy the inequality defined as subsolution. If it's finite everywhere, it's a subsolution. Now, it remains to prove 5. Okay, the first one was that phi x0 dot is a subsolution. So for this, we use the triangular inequality to get phi x0y is less than phi x0x plus phi xy. So this is equivalent to phi x0y minus phi x0x is less than phi xy, which implies, of course, that phi x0 dot is a subsolution. Okay. Now, for the other one, we now use phi u x0 is less than phi yx plus phi x x0, well, which is equivalent to minus phi x x0 minus phi yx0 is less than phi yx, which shows that minus phi dot x0 is a subsolution. So we always have subsolutions. Okay? They are just given by phi. And after that, we can, to obtain all phi solution in fact, that we can just take combination, convex combination of that, finite or infinite. Okay. Provided they are finite. Okay. Now, let me come to the pairs barrier. So this is the idea of Antonio, So we have to define the payouts barrier. For this, we introduce the concatenated cost by eta. For every eta non-negative, I'm going to modify phi to obtain a phi eta as a function from xx into r. So for that, I'm going to use chains. Recall that a chain is a sequence of points, x0, xn, with at least 2 points. It has only 1 point, it's a point, it's not a chain. Okay? The point x0 is called the starting point, and the point xn is called the ending point. So a chain starting at x and ending at y is a chain x0, xn with x0, x equal x0 and y equal xn. Now for a chain of points, we can define phi cost, C sub phi, just by adding the cost of 2 neighboring points along the sequence. Okay, so the cost for phi of the chain is the sum of phi of xi plus 1, going from I equals 0 to n minus 1, because I need the last one. Okay? Because of the triangular inequality, this is larger than phi of x0. Note the distance d is also semi-metric, so I can define the concatenated length LD, okay, for a chain in the same way. I take the sum of the distance of the 2 consecutive points. Okay, this is the way you define the length of a curve in geometry, by taking after that the soup of the whole sequences of points, okay, order of points on the curve. So in the sequel of this work, we'll assume that x has at least 2 points. I'm just going to give you the reason right away. If I have 1 point, I cannot have chains which are very big length. I only have a chain of length 0. Okay. But as soon as I have 2 points, I can find chains joining any 2 given points with arbitrary high lengths. In fact, if I have a pair xy in x times x, because x has at least 2 points, I can find a z different from x. Okay? And now I look at this chain, I repeat xz n time and end with y. So this is the chain of length 2 to n plus 1. What is its length? Well, if I take all these points here, the consecutive points, they have the same distance. Okay, it's the distance from x to z. So I get 2n minus 1 plus the last one is the distance from z to y. Okay, because dxz is not 0, the length of this chain goes to infinity. Okay, now this is the definition of phi eta for eta non-negative. Phi eta of xy is the infimum of the cost of chains for all chains starting at x, ending at y, with lengths larger than eta. Okay? So I take the cost, but I want to go along a long chain of points. It's always, of course, larger than phi xy. Now, because the distance from z to z and the phi of zz is 0 for all z in x, to compute phi eta of xy, I can restrict to chain such that 2 consecutive terms are not equal. I have to be careful here, but I have to add the chain in xx. In case, you know, the two points are are the same. Why is it that? Suppose you have two which are equal. I can erase them in the chain and still get a chain with the same cost and same length, except it is a chain if I still have 2 points. Okay? So the bad case is I have 3 points. If I erase, if I have 2 points, I erase, I end on just a chain with 2 elements, x, y, and if y is equal to x, I cannot say that the 2 consecutive ones are not equal. So the phi eta are called the concatenated cost associated to phi. Phi eta is the eta concatenated cost associated. So once we have the concatenated cost, we introduce the pairs barrier. Okay. Now, eta maps to phi eta xy is non-decreasing. Okay, because of the definition here. If I increase eta, I have less chains, so the infimum is higher. Okay? And because it's the limit exists as a function, as a number in R or plus infinity. And the limit is a SU. So the pairs barrier phi infinity is just this limit. Then the Aubry set is defined as a set of points for which the barrier from x to x is 0. Okay? And the phi solution, which correspond to the viscosity solution of the Hamilton-Jacobi equation, are defined in the following way. Well, they have to be solutions. So a phi solution is a subsolution. So a phi solution is a phi subsolution, which is, so subsolution so a subsolution satisfies that, yes? A solution should be a kind of an extreme case. So this means that for every x, you should have a y for which you have this equality. But if you say that, it's stupid because phi of xx is 0. So you could take y equal x. So you want to be careful. And this is why you have to introduce the concatenated cost and put here eta x positive. Okay, that will force much more. You don't want every subsolution to be a solution. So this is how it goes.